In this particular series, we are going to learn more about deep neural networks. But before jumping into the actual implementations and basically knowing what they are, let's start with certain basics, and that will be like a refresher before we jump in. So to start with, let's try to understand what a perceptron is. So if you look at this figure, so a perceptron can be represented by a very basic structure which consists of a set of weights, a constant, also called as bias, and a set of inputs. Now, what happens is these inputs, which are your features or which represent your features from your dataset, are multiplied with these weights and added with a constant term, also called as bias. And once this addition happens, which is also called as weighted sum, or you can just call it as weight into the feature addition, you basically apply a step function or an activation function on top of it. And then the output of this is your final output or the prediction. Now, if you look at this closely, it very closely resembles to a logistic function or what we typically do in while doing a logistic regression, right? There are features. If you look at the function at the top of the apps E, right, exponential function, there is minus W transpose X, right? The summation of W transpose X. So that W is basically our weights here. X is the feature, and we take a weighted sum, and then we apply the activation function, which is the logic function, on the sum, right? So that's what even a logistic regression function also represents. Now then, what is the need of a perceptron, or what benefit does it serve while we basically build a neural network based model? So perceptron is actually the basic building block of any neural network. A neural network is nothing but a collection of such perceptrons which also should have these step functions involved. Now I'll just come back to why this step function is needed in some time. But before that, let's basically understand certain terminologies. So for neural network, there is an input layer, there are nodes, there is an hidden layer, there are activation functions, and there's the output layer. So if you look at this figure on the right, the ones or the green, the blue, and the purple ones are basically our nodes. And in the very first layer is our input layer. The middle layer is the hidden layer, and then the final layer is the output layer. So what do you mean by input layer? Input layer is the very first layer which takes all the features as its input, right? So I am talking about input twice here. Like one is in the context of input layer, the other is the actual input, because every layer has certain input. Now what this input layer will do is it will apply a weight, which is basically a hyperparameter trained while we build the neural network, and then apply the activation function, which is then passed to the hidden layer. Now this output of the input layer becomes as input to this hidden layer, right? And then the hidden layer also has a set of weights which are basically trained during the model training process. And once it gives an output after applying the activation function, that becomes an input to the output layer. And then output layer finally aggregates all these together, multiply them by their weights, and use the final activation function. Now, depending on the type of problem we are solving, the activation function can vary, right? So just to give you some context, or people who are already familiar, if you are solving a binary classification problem, that will typically be a sigmoid function as the final activation function in the output layer. But if you are doing a multi-class classification, it will be a softmax applied over whatever the number of outputs you have, right? And if you have some regression problem which you are trying to solve, either if you can use ReLU, which will be between 0 to 1, or you can use a tanh as your activation function. So depending on the use case or the type of problem you are solving, you can change your output layer's activation function. Now, when we talk about a deep neural network, right? In this figure, we only saw one hidden layer. In a deep neural network, there could be multiple hidden layers. There could be 5 hidden layers. There could be 10 hidden layers, right? And as you increase the number of hidden layers, the number of hyperparameters would increase. Now you would be wondering why it would increase. Because if you remember, each of these nodes has a weight representation called as W, right? So if it's the first hidden layer and it's the first node, it would be called as W00. And if it's the second hidden layer, it would be called as W10 and so on. Similarly, if you go down in the same hidden layer, it would be W01, right? And once we basically train our network, So there are two main steps. One is a feed forward and the other is back propagation. We'll come to that in some time. You start learning these weights, and once you complete the whole training process, these weights are learned. And now whenever you get a new data point, you can just directly apply or do go in a feed forward fashion to get the output, right? So now that makes sense, right? When you increase the number of hidden layers, since the number of W increases, your number of parameters in the model increases. And as the parameters become more and more, your network becomes complex. So there is a chance that it might overfit if the number of data points are very less, or it can take like a lot of compute time. So whenever a rule of thumb, whenever you are actually training a deep neural network, we should always try to do a GPU based implementation. Now there are multiple libraries. I'll also come back to that in some time. But yeah, you can use GPU for a very basic network, or if you're setting some baselines, you can obviously opt for a CPU based computation, right? So just to summarize, a neural network is nothing but a set of perceptrons. There are five main components: input layer, nodes, hidden layer, activation and output layer. There are two processes. One is the feed forward and then the other is a back propagation. That will basically complete the whole training process. Now, one question which typically everyone has is, or is most commonly asked in a lot of interviews, is what is the need of an activation function? Now, activation function, so just imagine if there was no activation function, right? This is just a linear network, like a combination of multiple nodes put together. So without activation function, you would miss out on the very important, one of the very important components of a neural network, which is non-linearity. And how does non-linearity help? If there was no non-linearity, right, you could have just opted for a linear regression or a logistic regression based model. But with non-linearity, you can learn very complex functions. Now, what advantage does that give is, now if you remember SVM, right? A basic SVM is just a basically a plane hyperplane which separates two classes, like on a using a horizontal hyperplane, right? Or if you can talk, if you go into a very complex space, it is just like a plane divide between two sets of data points. Now, if you make it slightly more complex, you would opt for a kernel function like RBF or a polynomial kernel function. But that's it. That's the full limitation. But with simple, not I won't call it a simple neural network, but a deep neural network, you have multiple nodes, multiple hidden layers, and all of them put together along with non-linear activation functions. And this basically, when in conjunction, they can learn anything, literally anything. So neural network has been, or people who basically created the neural network claim that it can actually learn any kind of complex function, and that can be proven as well. So the fundamental or the main component of any neural network is the non-linearity, and it is brought by the activation functions we have. And there are multiple activation functions which are out there, and we would just come back to it in some time. So I think that's it from this video. See you in the next video. Thanks everyone.